Thank you very much, Mike. Ladies and gentlemen, it's my pleasure really to be here, and I would like to thank also NeaSpec for this opportunity, because they were talking me to really talk about this topic here, first of all, because it's something that concerns everybody of you. Kelvin-Probe Microscopy combined with s-SNOM, this means simply that we should really pay attention if we want to really go quantitative, and that's really true not only in the visible range when we use lasers for plasmons, but this is even more true if you go for subtle excitations like in the terahertz regime. And the goal of the talk is naturally to combine that into one in the instrument, and that's exactly what we also want to do together with NeaSpec. To give you more grounds on this, why this is important, is the following. We have recently succeeded in really going into the Ivy League in Europe, in Germany more to say, where we go for topological materials both on electrons, magnetics, spin-ons, whatever you like to, which means that the excitation energies goes down really from 1 electron volt down to below 1 milli-electron volt. And imagine that you have now really deteriorations which are in the order of 1 volt, 1 electron volt, which means you do a s-SNOM experiment and believe that your amplitude is really the right one. You're going to make up a very nice simulation, but your data doesn't fit. So that means simply that you have to really correct somehow for that. And that's exactly what we want to show. So our s-SNOM is basically 2 versions. One is 2 home-built versions actually that we see here, just cartoon a tip in a cantilever version together with a substrate. And we come in mostly with visible 2 terahertz, and we go, I will show you, below 1 terahertz even there. We recently bought also an s-SNOM. That means actually we have really managed within the last periods, meaning the last 2 years, to combine that to the nice mimic that we have. So this is exactly different from most of the presentations so far, which is our excitations, and that is we have on the one side a free electron laser undulators that is really tunable from typically 4 microns down to 1 terahertz. And a very newly one, fresher one, a super radiant source called TELBE, because it's terahertz, which consists of 2, a diffraction radiator, as well as a LINAC. To give you more grounds on that, and that's something you might really take home, is what are the benefits, what are really the specs of these 2 sources. And the one is actually, as you see, going down to really 1.2 terahertz, which means on the order of about 4 milli-electron LNGs. The other one has an energy that goes even down to 100 gigahertz, which is even more appropriate for some of the investigations if you want to go for spin investigations and so on. Also different is the bandwidth. This is a very narrow bandwidth, as you see, from 1%, so which means we can really scan narrow, and basically do some spectral scanning, which means really probe the full dispersion relations, while this one can be tuned between 20 and 100% in bandwidths, which means either you go full excitation, full bandwidths, or even narrow ones. Also, there are more subtle differences, and if you're interested into that, we are a user facility, like what Hans was already saying for the synchrotron. The same happens here. We're in Germany, and basically, if you have interest, then talk to me. Well, there's more on that, and Andre is really presenting a poster later this meeting, poster P16, where he goes now to use this FELBE, in fact, to go really time resolved. And you see exactly what the time repetition is. We have pulses of 1 picosecond, and we combine that with a tabletop laser. Well, these are not the only applications, because there are a lot of really users already applying for really beam time. We had fantastic collaborations in-house, then also with Thomas within Germany. We have collaborations within Europe, but also worldwide. So that's really a fascinating topic that is really growing. Fact is, we can go and do the 1 terahertz right now. So now, let me show one example before then going for the Kelvin, why this is really needed. And this is a recent example, and Hans was breaking the ice for the molybdenum trioxide already, because that's one of the rare materials that has anisotropy both in the X, Y, and Z planes. So what you see again is exactly a spectrum, as you see here, from about 6 or 7 terahertz up to about 12, which shows you the restaurant bands for the 3 different excitations, which are the 3 different epsilon directions. You see in red the Y direction, you see in green the Z direction, and in blue the X. And that means simply that you get anisotropy within one and the same plane. And the question was, can we measure that? That was also the question this morning. And fact is, yes, we tuned just our laser to either 9.22 or 1117, you name it, and basically measure there exactly what you want to see. And that's exactly what we see from these hyperbolic spectra. We see on the one side excitation, like you see here for that polariton, launch from the left side, or the other one actually launch from the bottom side with two different wiggles, which means two different wavelengths and hence two different lifetimes. So that's the sort of idea, the sort of measurement we can really do routinely. So now let's come to Kelvin. Why is this really important? Why would I like to talk about this at all here? And we have really done two recent publications on that, and I'm happy to really present the work that Tobias Nürnberg, that you can see him here, actually was really doing last year and have been written up in this APL photonics paper. And then in the follow-up measurement we did with Julian and also with the Taubner group from Aachen is on phase change memories. Just using exactly the same mimic, taking a Kelvin, an electrostatic measurement with the same tip in situ and do the same measurement. And what came out is basically this, that you can go from amorphous to crystalline, to re-amorphodize, to recrystalline, by simply combining these two, characteristic data, which is actually the s-SNOM spectra together with the Kelvin spectra. And only with this we were able to interpret the data correctly. So, we want to talk about electrostatics. And the most important thing, and this is exactly one step back, is 90% of our users are really, or we too, are using, so to say, cantilevers of this type, typically. Metallic, semiconducting, you name it. Now, this means that whenever you approach such a system, you want to make a measurement locally by this tip here, means that actually your substrate, whatever that is, two DMs, molecules, etc., you name it, is that we have always a chemical potential difference delta phi that we have here, right? And if you go for metals, for instance, silver and gold, typically the difference of that one is 1 electron volt. If you go for different materials like HBN, actually we get even larger values. Or in other words, we're having an extra potential U applied between that cantilever and our substance. You don't know about that. You don't care about it, in fact, because mostly actually, so to say, we're not compensating for that. There are many, many other, so to say, influences. This work function is one of the major ones that is always there. So we need to compensate for that. There can be interface dipoles, like shown here for these kind of buckyballs. There can be charge transfer. There can be polarizability. You shine with lasers on it, and this means you're going to create photovoltages, dipoles. And this all impacts, basically, on your fundamental, actually, excitation. So you see, basically, that we can apply also an external voltage, a DC and an AC voltage, just cartooned here, in order to really try to compensate for that. And that's exactly the goal. We want to get rid of that one. That means we want to make U to 0 simply because then the electrostatic force is 0, absolutely 0. Well, to measure forces in that sense is somehow tricky, and the larger forces are really for blunt cantilevers. And moreover, this whole cantilever has a total force, electrostatic force, because it's charged. So we rather want to go for a dynamic mode. We're vibrating the cantilever with delta F, and hence the same potential difference, so to say, goes into a frequency shift. So you just go and listen to your radio and basically measure the frequency. That's actually what we did. So what is that meaning? Well, this is exactly what you get out. This kind of voltage dependence, U squared, is always quadratic because Coulomb interaction is attractive interaction, and hence we go down from an apex here, always down in frequency, which means we're going to harden the system, right? So we want to go up to this point here, which is the apex, which means 0 electrostatics. We can compensate for that at this point. Please note that this point, the 0 bias, which is the external DC, is not aligned to this apex simply because we still have the work function difference, right? So we want to measure that now, and what we do is simply apply a DC voltage and then hence basically make a modulation on the left side, and you see nicely this is a slope being positive. You go to the right side, you will have a slope that is negative. That means we are very much slope sensitive in this system, which means we simply have to find, by adding an additional PI regulator, that point where the, so to say, slope is really 0. So we go for a slope 0, which also means we go for doubling the frequency at this mode. So if you put this whole schematic into a frequency spectrum scheme, you see that here, it is like this, that we have a modulation voltage, let's say 2 kilohertz, and then we have a carrier frequency, which is 151, and that's exactly like listening to radio, and hence basically you could really take that peak here, which is exactly an AM radio peak, AM Kelvin, please be aware this is really proportional to the force you have on your cantilever. And the force comes from the whole cantilever and everything. But if you go and now say we can add this F mod to the F0, which means we go for a sideband modulation. So we get sidebands up and down. Doesn't really matter which one you take because they're all shifted by the same 2 kilohertz here. And we get even second sidebands here, 2F0, and so on. What is the benefit of doing this at all? Well, the benefit is we can now really take a mimic, and there's some really modern type of lock-ins, FPGA programming, by really selecting that peak, for instance. We go now for measuring the force gradient rather than actually the electrostatic force. And why is this important? You know the force gradient is strongest at the tip apex rather than at the cantilever. And that's exactly increasing the resolution and the quantitative interpretation by orders of magnitude. So you can read up everything basically in a paper that we have been done a long time ago, but there's more in that because you can also go and measure the force gradient now at the second harmonic, second sideband, which gives you something like the quantum capacitance. You learn something about the local charging, for instance, dielectric, or the quantum capacitance in a graphene MOS2 bilayer. So we've really installed this mimic, and to really give you proof of that this is really needed and really working, first of all, let's show on a graphene. We have 1, 2, 3, 4 layers here colored really in an optical image. And you see nicely that topography gives you really false colors, black up to really bright colors. You step up. The step heights are not really correct, in fact. But if you go now for really applying this kind of Kelvin, you see nicely that in the surface potential, we can really nicely see the substrate in bright. And we see the first layer, second, third, fourth layer of graphene with different colors, which means different negative potentials. So we know exactly how much charge and how deep, so to say, the potential is really dropping. And this typically, as you see here, about 100 millielectron volts. So even for graphene or 2D materials, it makes a lot of impact there. Second example, lateral resolution. We take molecules, which are typically these copper porphyry molecules, typically 1 by 1 nanometer in size, which have 4 legs. You put them on a copper surface. This is ambient room temperature. And then you go with your Kelvin mimic and say, well, can we see that? And in fact, the topography shows you, well, only patches of these kind of molecules, while actually the surface potential by exactly this kind of FM mimic gives you an insight even showing where the charges sit within the molecule. Or in other words, we get a very good spatial resolution with a very good, combined with a very good actually energy resolution in that. So now let's apply that for s-SNOM. Let's go for s-SNOM, and this is exactly what Tobias did. He took that mimic, this is exactly the electronics he was applying to put that electronic with a modulation voltage on the cantilever. We have our oscillation of the cantilever here. We have a beam deflection unit, and basically what we're looking at is now exactly the sum or the difference frequency. So exactly the sideband, the first sideband, which is exactly proportional to the force derivative. We take this into a PI controller, which is going to deliver a DC voltage that is controlled back into our cantilever in order to balance off that in the end we end up really in the apex of our parabola. As a test sample, we have been really using here a p-doped silicon substrate that has really trenches of silicon dioxide in it, and on the top of that, at one side, a gold contact in order to now flip the cantilever once on the gold contact for testing and really installing everything, and then really do measurements. Please note that we can apply also additional voltages then to the substrate for testing. Okay, first test, we go and make retract curves. That's what everybody does. So we take the tip, basically pull back, see where we have a near field, and see actually also what is the impact on that near field when we apply different voltages between 0 and 4 volts. And you see nicely what we have done is actually here, we pull back that tip on top of the gold contact, and we see nicely starting by the 100%, which is actually the bias of 0 volts, that actually you see a very dramatic actual dependence. We see an exponential decay as we are used to see. Well, not knowing what voltage you apply to your cantilever, you could get any of these curves, and you see nicely by now really putting them together in the same really manner. We see that already by 1.6 volts, which is typically the surface potential difference, you get a reduction of your amplitude, of your near field amplitude by 50%. What it means is simply that your electrostatic forces is damping down your cantilever, which means in the end it's not as freely oscillating, but gets broader in its Q value. So what we need to do is actually crank this up, so to say, to top by switching on the KPFM regulator. And that's exactly what we do. You see nicely that all these curves now fit together, independent of what voltage we apply. Second experiment, we go for line scans. Well, we take the test sample, we scan along that line scan, which was exactly made of p-doped silicon and silicon dioxide and so on. At the same time, what we do is apply a certain modulation voltage, US. You see this triangular voltage here, zigzag, simply to test how good is our regulator working. You can really test the speed of your PI control with this. And that's exactly what we've done. First of all, we have switched off the regulator. You see the red line. This is the control KPFM voltage, 0, which means everything of that is added to the A topography. You see these quasi errors we do here, and also to the near field signals. The dashed red line is the correct one, while the black one is the measured one. So we see deviations. Generally, you don't appear to see that because you never know how much that is. Now we switch on the regulator, and finally you see nicely you can follow exactly these contours of our applied voltage. Depends on the feedback and how fast you are. Okay, to give you numbers, we can go up to 3 nanoseconds at the moment, so this is really fast. So that means simply that now the topography on one side as well as the near field signal are really quantitative. So you know exactly how much your cantilever oscillates. You know exactly that this structure is free of artifacts, at least electrostatic ones. Let's go for imaging. And this brings us a new thing, which means that now we can also take this additional information of Kelvin that we have been measuring. We have 3 channels here, topography, we have now the near field, and on top of that, we have now this for free, this Kelvin potential. We take the output of the PI, put this into a channel, and what you see nicely is really imaging exactly. And you see different colors, which means bright and dark for different crystallized areas. So we see nicely by taking a cartoon, or let's say cross sections, that we have 4 different regions. This is more that Julian is going to talk about possibly in a little week. We have amorphous regions, we have crystalline regions, we have re-amorphized regions, and we have recrystallized regions. So this means simply that we can really, by taking all these signatures combined between blue Kelvin and reddish, the near field optical amplitude, 100% identification of these phases. So this is exactly what has been done on these chalcogenide phase change memories. With this, let me start with a summary. What I wanted to show to you is exactly, first of all, that we do have an operation really of a really operating terahertz s-SNOM. We can really couple that to these fancy really acceleration units that we have down to really, in fact, 100 gigahertz. I showed you how this principle of Kelvin compensation works and what the best way is, in fact, to go for this sideband regulation. We've done all the other testing of other Kelvin tests as well. I call it AM. There are other ways how to go for higher harmonics of the cantilever oscillation and so on. They're all not as good as this sideband principle that I showed here. Thirdly, I showed to you also how we do with this by going for retract curves, for line scans, and finally imaging. And last but not least, I showed to you also that this is not just fancy, but really gives you also additional information. And with this, let me thank you. Thank you much.